Hello, my name is Carlos Hernández. The title of my presentation is a simple and fast BiObjective search algorithm. This work was done with William, Jorge, Han, Luis, and Sven. BiObjective search has many interesting applications. For example, path planning in robotics, hazmat transport in cities, cycling, and vehicle routing. In all these applications, BiObjective search use two objective functions instead of one. For instance, in path planning, in robotics, can use distance and battery consumption, and in cycling, distance and driver safety. Okay, in BiObjective search, we have two objective functions, G1 and G2. For instance, in this plot, we have these two functions, G1 and G2, that represent two solutions, for instance, that have two costs, G1 and T2. Here in the plot, we have several solutions. The point are several solutions. For instance, here we have a solution that have a value of 10, 8. We have, in addition, a dominance relation that when for vector AB dominate vector A prime, B prime, if and only if A is less than or equal to A prime, or B is less than or equal to B prime, and IB is not equal to A prime, B prime. Okay. For instance, here we have a vector 10, 5, that this is this solution. This solution dominates 10, 8 because 10 is equal to 10, but 5 is less than 8. Okay, and some solution, for instance, all the solution that this 5 solution correspond to the optimal Pareto set that are all non-dominate solution in the set of solution. Okay. BiObjective search algorithm does a dominance checking process. This process has a very big impact in performance, and all the algorithm do the same, a similar process, including NaMoA that is one of the state of the art. How this process works, the dominance checking works in the algorithm of BiObjective search. Basically, here we have a state that state S. Okay, a new path arrived to S, or the search reached S with a path of cost 3 and 9, and then a new path arrived that have cost 4 and 8, and this to be sure that this path is not dominate. We need, or the algorithm needs to compare this solution with all previous solutions founded. Okay, for instance, okay, 4, 8 is not dominated by 3, 9. When 7, 5 arrive, we can see that this 7, 5 is not dominated by 3, 9, and then it's not dominated by 4, 8. And 7, 4 is not dominant for 3, 9. It's not dominant for 4, 8, and for 5, 7. But now this path H6 is not dominated by 3, 9. It's not dominant for 4, 8. It's not dominant for 5, 7, but it's dominate for 7, 4. This solution is not included in the no dominant path set. Okay, this process take linear time in the number of no dominant paths. Okay, for one state. Okay, what is our contribution? We present a new BiObjective search algorithm. The main feature of this algorithm is that the dominant checking process is done in constant time instead of linear time. That this is this feature represent the main characteristic of our algorithm. And this algorithm is simple and resembling standard A star. Okay, we find the Pareto set order of magnitude faster than the other algorithm of the state of the art. Okay, how our dominance checking process works. Okay, we use for the search H1, H2 heuristics that are consistent, and the open list is sorted lexicographically by F1 and F2. Okay, for each state in S, BOA maintain a G2 BiObjective A star maintain a G2 mean value of S. Okay, and how it works? For instance, we have the same example, and now the empty is the non-dominant part of S is empty. The G2 mean of S is infinity. Okay, and okay, the first path arrive. Okay, the search reach is through this value, and then a second path of value for H reach S. Okay. Okay. We use, if you see here, 4 is bigger than 3, and of course we use a consistent heuristic. The G1 and the open list is sorted by F1, F2. That means that the G1 of the solution ever increase. For instance, 4 is bigger than 3, and the next solution will have a bigger G1 value. Okay, because the consistent of the heuristic. And the only way that we obtain a no dominate path is when the G2 value of the new path, in this case for H, the G2 value, that is H, is less than the G2 value of the last path founded. For instance, here the G2 value of the last path founded is G2 mean, that in this case is 9. And if we see, as we see, H is lower than 9, and we can add in a safety way this path to the no dominant path. Okay, and now a new path arrived, and we can see that 7 is lower than 8, and of course we can add this path to the no dominant path set, and then a new path arrived, that is 7, 4. Yes, 4 is lower than 7, and we can add this algorithm, and we update the G2 mean value to 4, and then a new path arrived, but this path have a G2 value bigger than G2 mean, and we can and we don't add this path to the no dominant path. Okay, this check take constant time. Okay, it's because you need only to check to compare the G2 value of the new solution with the G2 mean of the S value of the S. Excuse me. Okay, and this is our algorithm. If you see this check, this check is doing in here and here in line 20, in line 11, and in line 22. And as you see here is only an if condition. Is a very fast. It's a constant time process. Okay. BiObjective compute a cost unique Pareto optimal solution set. Okay. And we compare the algorithm with the state of the art algorithm, and we use 5 roadmap from the DMAS benchmark. Okay, here you see the result for New York and Florida. The roadmap of Florida is around 4 times bigger than the roadmap of New York. And in average, you can see that BiObjective is the best performance algorithm, and ever solve all the problem. Okay, in a bigger map, you can see here we are the instance are sorted by difficulty, and when the instance is more difficult, we scale better than the other algorithm. And finally, as conclusion, we present a BiObjective algorithm that is faster than the state of the art, is order of magnitude faster, and as future work or future direction is to work in bounded optimal BiObjective search and multi-objective search. Thank you.